Welcome. I'm going to tell you a bit about computer architecture for security. So the title's really motivated in part by a very good paper, The Eternal War in Memory. And this paper and other works have identified that a large number of security vulnerabilities are all down to memory safety violations. They're not down to problems in the crypto or problems in cryptographic protocols. It's actually bugs in memory safety. And that's what I'm going to show you today is how to develop computer architecture and associated software techniques to eradicate these bugs. And these are pretty nasty bugs. I mean, WannaCry's been in the news very recently. A ransomware attack on Windows, it affected a lot of machines in the NHS, the health service in the UK. Heartbleed, which I'm going to tell you more about now, is both from just a couple of years ago, and this is a bug in the protocols used for HTTPS, the TLS protocol used to do web transactions. And with this Heartbleed bug, you could impersonate people, and you could break into banking systems and so on. So let me just explain to you, to give you a bit of a feel of what the challenges are, let me just explain this Heartbleed bug, this vulnerability, partly because it's a relatively easy one to get your head around. So with Heartbleed, the actual security protocols component was just fine. What the attackers realized is that there was a little heartbeat message that was sent out between the client and the server just to keep the connection alive. Okay, so just using this XKCD cartoon, basically the client says, "Hello server, you still there? Say potato, it's 6 letters long." And the server says, "Potato, jolly good. Okay server, now say bird, 4 letters long." The server says, "Bird." Then you think, okay. "Hello, server. Say hat. It's 500 letters long. Trust me, it really is." And the server says hat, and then it keeps saying what else is on the stack. And what's on the stack includes secret key information and all sorts of stuff. So this is just ridiculous, right? And it's embarrassing. I mean, we keep getting memory safety bugs and issues again and again and again and again, and it isn't solved. So what went wrong and how do we do better? Well, the classical answer is that the programmer forgot to check the bounds on the data structure. Stupid programmer. And in this particular case, if you look at it's a one-line fix to sort of check payload lengths and so on. But actually, if you look at that one line of C, it's not desperately intuitive. It would be very easy to get it wrong. It's very easy to forget to put the check in the first place. So our answer really is very often this bounds information is implicit in the code. The programmer declared some data structure or allocated some piece of memory, and implicit in doing that action is they've said what the bounds should be and what the access right should be. So what we do is we're aiming to preserve the bounds information during compilation, and then using our hardware, we have a processor called CHERI, to dynamically check that bounds information with very little overhead. And we're also going to guarantee pointer integrity and provenance. So what I'm going to do now is tell you a little bit about this CHERI architecture. Normally when I give this talk, and I have rather longer, I talk in depth about integrity and provenance and the principle of least privilege. But today I'm just going to go bottom up. Let's just go for it because we don't have much time. So what have we actually done? Well, we start off by introducing a capability. Now, ideas of capabilities have existed for a long time, and there are cryptographic capabilities and all sorts of things. But the capabilities here on CHERI are in-memory protection capabilities. So a CHERI capability is a bounds-checked pointer with integrity. And that capability can be stored in memory, or it could be held in registers. In our current implementation, which actually is a MIPS-based one, we introduced a completely separate register file, a bit like adding floating point registers in order to store these capabilities. But we now think it's probably better to, say, extend the integer register file. Anyway, the representation is an address, so we've got 64-bit address, 64-bit machine, and then we add another 64 bits, and that includes permissions, bounds, and an S-bit, which I'll refer to in a bit. I'm also going to tell you a little bit how we compress the bounds in a moment or two as well. So we want bounds for the top and the bottom of the region of memory that this refers to, and then the permissions are sort of things like read, write, execute, software managed permissions, and so on. We also very critically add a hidden validity tag, which we sometimes also refer to as an integrity tag. And this is absolutely critical to security properties. It means that you cannot fabricate one of these capabilities in memory. You can only derive a capability from another capability. We'll see in a minute that that's very important. The actual bounds component is really very simple. It just gives you, the bottom and the top of the region, and the address points somewhere inside that region. It can, in fact, also point outside that region. We have looked at a large corpus of C code and discovered that C programmers do all sorts of horrible things, and they do all sorts of horrible pointer calculations, and in practice, even though the C standard says that you should not do it, because you can get away with it on current machines, they do. So we've had to deal with this address going outside bounds to some extent during address calculations, but as soon as you dereference that address, so you do a load or a store, the bounds are checked. We have to add a few new instructions. So we need to have variants of load and store instructions that use capabilities as the reference, and that they do a bounds check during access. And that bounds check can happen in parallel with L1 cache, so that's easy. We then add some instructions to manipulate capabilities. So you want to be able to decrease bounds, and you want to decrease permissions and adjust the address and extract the fields. Decreasing bounds and decreasing permissions is really quite critical, and in particular we don't want to be able to increase bounds or increase permissions. We want a monotonic decrease, and that has to be guaranteed by the hardware, and in fact we've done quite a bit of work on formal verification of the instruction set to guarantee that properties, because that monotonic decrease in writes is critical for the security argument. And these sort of mechanisms apply to user code, and it also applies to supervisor code. Okay? The instructions simply don't allow you to increase permissions. Okay, how do we then apply this in practice? Well, we can start off with unmodified code, all the way on the left-hand side, so that's where we are today, where all pointers are integers, and they're interchangeable, and you can overwrite them and corrupt them, and the processor will never notice. We can go all the way over to the safe world on the right, where all references are capabilities. And we've also got the hybrid case in between. And in terms of actually transitioning this sort of technology, it's quite important that the processor can handle anything on that spectrum. Okay? So we've got to be able to take existing applications, still be able to run them. And in order to do that, we actually have a default data capability, so that all memory accessors still refer to a capability. It's just that there's a default one. And the program counter for any of this code is also a capability. In hybrid mode, when you're actually writing C code, you have to be explicit about what's a capability and what's just an integer pointer. And we've got compiler support for that, so you can make choices. And that works very well, and it's quite good for interfacing sort of old code and new code together. But where we really want to be is pure capability code where all pointers are capabilities. And then we get ubiquitous data and pointer protection. Also interestingly, it turns out, and somewhat to our surprise, that actually recompiling swathes of C code just works in the pure capability case. Okay, so the migration path is actually pretty easy. And we have good compiler support now that generates code for all of these different cases. Okay, the other thing you do need, if you're dealing with pure capability code, then all your pointers are capabilities. And if you want to do an operating system call, you may be using a legacy operating system. And so one of the things we've looked at is how do you do that ABI layer. And so we've got something called CheriABI, which is a bit like a 32-bit compact layer that you'd put on top of a 64-bit operating system. And my colleague, Robert Watson, is going to talk about that tomorrow in the security session. And he's far more knowledgeable on the software side. He's led all the software, basically from the instruction set up on this project. So he's around. So what I'm going to talk about now is how these techniques mitigate various vulnerabilities. So we use capabilities for bounds checking and for integrity. So if we assume we've got pure capability code, all pointers are capabilities, the compiler can derive bounds. So if you've got a data structure, you allocate something on the stack, the bounds are established. If you simply malloc a region of memory, that gets bounded. And we also get very strong pointer provenance. So for instance, if the compiler subsets a capability to point to the heap, and then further subsets that heap capability to point to other structures on that heap, you get this nice tree structure. And actually, something to our surprise, even just taking loads of existing C code, that provenance structure just works beautifully with existing code. It doesn't break anything. We do similar things with the stack as well. So we get all sorts of protections here. Firstly, that hidden validity tag gives us integrity and provenance. You can't just arbitrarily create a pointer out of thin air and dereference it. It's not allowed anymore. We have bounds checking, and this means that we can avoid taking a reference to one object and using it to refer to another object. We've got this monotonicity property, so that if you've narrowed the bounds down on a capability, you can't grow them back up again. And all of these things then mitigate buffer overflow and buffer overread vulnerabilities with no change to the code. So things like Heartbleed just vanish just by recompiling the code. We can also take it further. We use these capabilities to refer to code pointers. So capabilities can be used for return addresses, and this helps us mitigate attacks like return-oriented programming and jump-oriented programming attacks. You may be oblivious to these sort of attacks, but actually on current systems, techniques like address space layout randomization are routinely used. I was looking, for instance, on Ubuntu Linux recently, and Ubuntu Linux compiles all the standard tools with address space layout randomization. And the idea with this is that they sort of manipulate where the linker places code in order to make it more difficult for the attacker to stitch together little bits of code to do something malicious. But it's a very statistical technique, and in fact there are ways around it. It just takes a bit longer. What we do instead is a return address when it's placed on the stack is a capability. And it's an executable capability. An executable capabilities are very difficult to just magic out of thin air. And in particular, if an attacker is causing or attempting to cause a buffer overflow, and overflow that return address on the stack, that capability will get overwritten, the validity tag will get cleared, and that return address is no longer a valid return address. So if it gets mapped into the return address, register and put in the PC, you get an exception. So it mitigates all those things. So if we sort of summarize the protections, we've got the integrity, we've got the bounds, we've got monotonicity. We manage things on the code side as well to help with control flow integrity. We'll make that more robust. And we've also got permission bits to help us avoid mixing up code and data. We've got valid user space pointer set. So pointers are not guaranteed using, pointers not generated using any pointers that are not generated using the appropriate deriving rules are no longer valid pointers. We get pointer privilege reduction. So capabilities allow pointers to carry specific privileges, and those can be minimized. And this is foundations for high-level models such as compartmentalization. I'm going to quickly explain compartmentalization to you. So we have a slightly different capability format for what we refer to as sealed capabilities, and I'll explain how we use these on the next slide. So sealed capability, we basically add this extra field called the object type, which in our implementation is 24 bits of data, and we further compress the bounds to give us space. This is a non-dereferenceable capability, so you can't use it to refer to memory at this point, or you couldn't use it to refer to code. Okay, the object type compressed, and we set the sealed bit. So, give you a bit of an intuition how this works. If we want to set up a compartment, we need a sealed code capability and a sealed data capability. A CCall, so we've got a new instruction for a capability-based call, then checks the object types, and if they are identical, then the hardware unseals those capabilities, so you then end up with a program counter capability to the code and a default data capability to the data. Okay, and so that's basically created you a sandbox in which you can execute. This is quite a powerful technique. So the question is, does it work? Well, first we made it work on a prototype. So we have an FPGA-based prototype. We built a sort of tablet-type demo. We were funded by DARPA, and DARPA likes evaluation teams. They call them red teams, and we had MIT Lincoln Labs, who were a pretty ferocious lot. And we turned up to one of the DARPA meetings, having spent hours doing our own demos, and their MIT Lincoln Labs were with one of our setups running on an FPGA saying, "Oh, look, CHERI mitigates heartbleed." And we just had to recompile the code. It was the best demo ever. Let's give you some performance numbers. So the bounds checking is incredibly helpful, but the performance win is when we start doing compartmentalization. And an easy way of drilling down to the performance is to look at moving data from one compartment to another. So here we've got a log-log plot with the payload size when we're moving things into a compartment on the x-axis and the execution time on the y, which is also on a log scale. So current techniques, current best practice is to use process-based compartmentalization, and this is what you get inside things like iOS in your phone, where they run all sorts of different bits in different processors at quite some cost. CHERI-based compartmentalization, however, is orders of magnitude more performant. And in fact, we start getting much closer to just doing a function call type costs. And that's just for moving data between one compartment and another. It also scales phenomenally better when you have large numbers of compartments. And so that's the real big performance win. If we just look at the memory protection mechanisms, so this is just doing the bounds checking where we have bigger pointers and we're doing all this bounds checking. Well, for lots of things, if you compare CHERI 128 with the baseline MIPS, they're almost identical. There's almost, this is normal pointer code. There's almost no overhead at all. If we look at very, very pointer-heavy benchmarks, then we do see some performance impact. And in particular, our original version had a 256-bit wide capability, which was enormous. And so we compressed that down. Right, looks like I really ought to finish up. I have some microarchitecture stuff on compressing capabilities and doing efficient tagging, but I'm going to skip over those in the interest of time. We've been working very closely with ARM, so for instance with the tagging we thought, it's only a couple of % overhead, but ARM said, you should do better, so we did. And we have a paper on that at ICCD. So let me conclude. Fundamentally, I think this CHERI-based mechanism is going to win the war in memory. It provides hardware with much more semantic knowledge of what the programmer intended. And it pushes us to what we refer to as the principle of intentionality. In other words, you're more like you run the code in the way the programmer intended, not the way the attacker tried to trick it. We get very efficient pointer integrity and bounds checking, so we should just be able to completely eliminate buffer overflow and buffer overrun attacks forever. And it provides us with scalable, efficient compartmentalization, and then allows us to apply key principles like the principle of least privilege, which allows us to mitigate both known and unknown attacks. And I think with that, I'll leave it at that slide. Thank you.
Thank you.